Okay, so we're on to secondary compression. So this is one of those extra topics that somebody's going to look at. We'll talk about that next lesson. Okay, so what are our goals here? Describe the concept of secondary compression. Oh, I said secondary consolidation, or I should say secondary compression. And when I say the micromechanical process, I just want you to qualitatively talk about, well, what's actually happening that we continue to get deformation when there's no change in the effective stress? Because the load on the skeleton is not changing during secondary compression, right? So what's going on? And then, most importantly, given the laboratory data, calculate C sub alpha. And then another thing that's really important to understand is that secondary compression can actually affect the way the laboratory test data. One of the reasons on some of those test data that you have in the lab from that lab data don't show the inflection point in the curve is because of secondary compression and some effects there. So we're going to talk about that. All right, and we probably won't get to that part today. So this is a repeat. We've talked about this already. The total volume change comes from two components. We talked about this already today in a slightly different form. There's a change in volume due to a change in effective stress at a given time times the change in effective stress as a function of time. And the second one is a change in volume versus time at a constant effective stress. Now notice that these two are in the same equation. Right, so at any given time, both these components can be there. That's an important thought to think about right now. At any given time, there's nothing so far I've said that said one goes on and all of a sudden it turns off and the second one starts. These are both functions of time. Right? One's due to a change in effective stress and one's not, but they're both a function of time. So the primary compression is that volume change due to a change in effective stress. That's the first part. This is the primary consolidation. We did this in a slightly different form just a minute ago. And that secondary compression is a change in volume at a constant effective stress. So, and we just did this. So I'll go very quickly through this. So Tsuchisagi's theory says that we get the dash curve when we look at it. We realize that we get more compression at the end than we get from Tsuchisagi's theory. And Tsuchisagi's theory says it takes forever for the pore pressure to go away. But we observed that there is a point where the pore pressure goes to zero, and that separates secondary compression from primary compression. The slope of that curve, I'm going to very carefully, now this is a deformation curve, right? This is not void ratio and it's not strain. This is deformation versus a function of time. That's what I can call S sub alpha. So that's the settlement as a function of log time during secondary compression. Now we know at this time that there is no how do we know at this time that there's no primary consolidation going on? Well, yeah, well, because what's the change in effective stress as a function of time there? Zero. So this term is equal to zero, right? So any deformation after the pore pressure is equal to zero, any deformation has to be secondary compression by definition. What we don't know, and which will be important later, what we don't know is on. Oops. What we don't know is in this part of the curve in this direction. Is there any reason there can't be secondary consolidation going on in that direction? None. So the only time we really know what's going on with secondary compression is after the excess pore pressure is dissipated. That's an important concept, and it's going to affect a lot of the ways we interpret data. So S sub alpha is just the change in settlement. In that case, it's just the deformation of our sample, d log of time. So don't confuse, you guys, a lot of you made some really simple, silly errors about C sub C. This is one of those C sub C things. This is change versus log of time, right? It's not the change in deformation versus the change in time. It's the change in the log of time. Okay, so C sub alpha, the original definition for the characterization of secondary compression is C sub alpha. This is the original one. It was defined as a change in void ratio as a function of the change in log of time. There's a lot of confusion about this, and it's used incorrectly many places. Whoops. One of the reasons I pointed out is because in DOS it was wrong, and I forgot to update these ones from DOS. I apologize for that. There is a term epsilon sub alpha, which is this is the equivalent. Remember the difference between C sub C and C sub C epsilon? C sub C epsilon. This is the same concept. Epsilon sub alpha is C sub alpha over 1 plus not E naught, but E primary, where E primary is, I don't know if I define this in a second or not. No, I don't. EP is E at T100. In other words, the E at the end of primary consolidation. This is completely analogous to the way the difference between C sub alpha, C sub C and C sub C alpha, C sub C epsilon, excuse me. So lots of times people use epsilon sub alpha and say C sub alpha, and they're not correctly using them, but so be careful about that. There's a difference. And then the one we calculate in the lab test, well, the one we measure directly in the lab test is S sub alpha, because right in the lab test is deformation versus log time. So you got to take the lab data and you got to convert it correctly into either C sub alpha or epsilon sub alpha. So don't confuse those. They're often confused. So once we know C sub alpha, and we can now calculate the secondary consolidation we expect to see in any time after primary consolidation. We do this in a very simple fashion. We just say that the secondary compression is going to be C sub alpha over 1 plus E primary, or if we want to put epsilon sub alpha in there, we can do that, times the thickness of the layer when secondary compression is started, times the delta log T, which is going to be log of whatever time we're interested in, divided by the time at the end of primary consolidation. It's not the time at the beginning, it's the time of primary consolidation. Now there's an implicit assumption here that we're going to calculate the secondary compression as if it didn't start until the end of primary consolidation. Okay, that has implications later, which I've already alluded to the fact that there's implications later. So what we're assuming is the soil goes through primary consolidation. At the end of primary consolidation, magic, it's all done. It goes into secondary consolidation, and we're going to calculate secondary consolidation using C sub alpha or C sub or epsilon sub alpha, whichever way we want to characterize it. It's a very simple calculation. It's a very simple concept. It's not clear it's correct, but this is the simplest way of doing this. So one of the exercises I want one of the teams to do is calculate C sub alpha on this and calculate the secondary compression and see if you got any significant secondary compression in this project. Okay, some characteristics of secondary compression. So secondary compression is obviously something that's initiated from primary consolidation. If we see an existing deposit of clay and we go out there and measure displacements, if there hasn't been something to disturb it or some load applied, it's not settling. It's happy. It's just sitting there. So obviously it's generated because some kind of primary consolidation it was started, or else we'd see creep all the time. And we don't necessarily see creep in soils and soil deposits. They've been geologically deposited. We don't see things sinking unless we've gone out there to load them to do something to them. So it's obviously a natural response to whatever disturbance we did to the soil structure. So soils, they're not human, but they have character. They've got character and I don't know, personalities and things. And so when you go out there and mess with them, you go out there and mess up soils, you're messing with their character and their personality. So when we go and load a soil, we break up whatever structure that soil had that it was happy with. It was perfectly, for however many, whether it's 100,000 years or a million years or 2 million years, that soil was really happy until we came along and built an embankment on top of it or something. And so we're changing the structure of the soil. So that causes rearrangement of the soil particles. and there's going to be a new structure of the soil particles. Now, you read Mesri and Godlewski, is that the right name? I can't ever say that name. Where we talked about the locking and unlocking of granular soils. Right? We've talked about edge-to-face flocculation and structures that you get in clay soils. And so those all happen. They take time to happen. And once those structures are created, there's some energy level. If you want to think about it, you think about this in entropy terms. There's been some energy dissipated in the material to come to that arrangement of particles that it's happy at. And it's happy. It likes it that way. So we're going to go and disturb it. We're going to go disturb that soil, and it's going to go primary consolidation, which we understand. There's a stiffness to the soil skeleton. It's nonlinear, but there's a stiffness to the soil skeleton. And once that soil skeleton is strained enough to take all the new excess, the new change in effective stress, the skeleton itself doesn't need to consolidate anymore to take any more load. It's taken the load. But it doesn't like that new structure anymore. I mean, it wants to rearrange itself into another pleasant, happy, contented structure. And you could think of it in philosophical terms if you want to, or you can think about it, it wants to get to it, that disturbance is, we put energy into the system, and it wants to get to a lower energy state. If you want to think about it, you can think of it in terms of entropy terms, but it's going to rearrange itself to get into a more stable structure. And that's what's going on during secondary consolidation. The other characteristic of it is there's no reason to think that it starts after primary consolidation. And if for no other reason, think about it this way. So let's assume I have a singly drained soil layer. So it's drained on the top and not on the bottom, right? And let's assume that this was my initial conditions. This is UXS initial. And at some time afterwards, what do my isochrones look like? Any time afterwards, any significant time afterwards. Okay? It will look something like this, right? Well, what's the degree of consolidation of that part of the sample at the top of the layer at that time? Right at the top of the layer, how consolidated is the soil? What's the excess pore pressure at the top of the sample? 0. So it's 100% consolidated. So even if you think that secondary compression doesn't start until after primary, even if you think that's true, the soil isn't all consolidated at the time. So let's just for a second assume that for some reason secondary compression doesn't start until primary compression is over. Well, for my soil layer, when does it start? Well, at the top it starts right away. At the bottom it doesn't start till I reach 100% consolidation for the entire layer. So even if you think it doesn't start at the same time, it doesn't start till there's 100% consolidated, well, the clay layer doesn't reach 100% consolidation all at the same time. The top reaches it right away. And there's no reason to think that as soon as you disturb the soil structure, there's no reason to think it doesn't start, whatever this process is that's creep, there's no reason to think that it doesn't start while it's also undergoing primary consolidation. In fact, it's pretty clear from the evidence that that's true. And I'm going to stop at this point. If the secondary consolidation is initiated by primary consolidation, and it's initiated because you're disturbing the soil and you're rearranging the soil particles, then the more rearrangement and the more disturbance to the soil particles, it's logical to think that that's going to cause more secondary compression because there's more disturbance. And so the greater C sub C, in other words, the steeper the compression curve, the more disturbance, the more strain you're going to have during primary consolidation. And so there's a logical reason to think that might also generate more secondary compression, and we'll talk next time about the evidence for that. So I think the take-home points of this, I think there's two really important take-home points of this. Is secondary compression, well, first the definition. Secondary compression is strain that occurs at a constant effective stress. That's one. Two, the only time we can observe it by itself is after primary consolidation is done, because that's when there's no change in pore pressure. That's the only time we can observe it. there's no reason to believe that it waits until primary consolidation is done. And even if you think that's true for an entire layer, it can't be true because the top of the layer consolidates way before the center of the layer or the bottom of the layer if it's undrained. And so the amount of, and the secondary compression is happening because we've disturbed the soil in its initial state, its initial particle rearrangements. And once it's through primary consolidation, it still wants to rearrange itself to get to a lower energy state, a lower entropy if you want to think of that, or just to get more comfortable if you want to think about it philosophically, I don't care. Then that's kind of the source of secondary compression. And so next time we'll look at this potential relationship between C sub alpha and C sub C, and you got a paper by Mesri to read on that that's like the classical paper on this that everybody needs to read. So that's I think that one I assigned for a one-page summary. Okay? I will see you guys on Thursday. Okay, so last lesson we'd done our introduction to secondary compression, basically just defined it. And remember we said there's three different ways this information can be presented. The original definition, characterization was C sub alpha as the coefficient of secondary compression. And that's defined as the void ratio change versus log time. There's obviously an equivalent epsilon alpha. This is very analogous to C sub C epsilon, which is defined as, well, which is equal to C sub alpha over 1 plus E primary. It's E primary instead of E naught because we're using this concept that the secondary starts after the end of primary. And then finally, in terms of settlement, it's the change in settlement versus log time. And that'll be important, one, to calculate settlement in the field or to calculate C sub alpha during the lab test itself. And then we talked about this already. So once we know C sub alpha, we can estimate the secondary settlement by just using this equation. And notice that the T is the time at which we want to know the secondary, and TP is the end of primary. So this equation assumes all secondary compression occurs after the end of primary consolidation. We alluded to quickly how that's not necessarily reality, but that's the assumption we made. And it works okay in some cases. There's some cases where it won't work. It works okay in most cases, I should say. And then we went over these characteristics of secondary compression. Right? So we're all caught up? Okay. All right, so I believe Mesri 73 is the one I assigned to you for a one-page summary, right? Okay, so this is the classic paper on secondary compression. And I'm going to take you through this one, and I'm going to take you through a couple other of papers of Mesri's and some of his students to show, because like a lot of times the first one is like the seminal paper, but it's been updated and there's better information. But the first one is the one where the concepts are there that you need to learn. So this chart, this figure you're going to see in all kinds of texts. It's like, you know, one of those really popular figures. And in this one, Dr. Mesri is plotting epsilon sub alpha. It's important to know that's epsilon sub alpha. You'll see that misprinted in many, many texts as C sub alpha. In fact, I forgot to look in Holtz and Kovacs whether it's C sub alpha or epsilon sub alpha. But oftentimes that's one of those, I told you lots of times people confuse those two. And it's plotted as a function of the natural water content, which doesn't necessarily make any sense why. So if a soil has a high natural water content, well, that means it's more compressible. So if it's more compressible, then maybe it has a higher secondary compression. So maybe from that standpoint it makes sense, but it's not a particularly good measure. But there's a reason that it's not a good. The reason that it was used because in 1973, Mesri didn't have a lot of really good data where he had really good measurements of C sub C. You know, if you think about the data that you've got for your project, right? You got two consolidation curves, right? One of them looks pretty good, In other words, you got a real nice sharp break where there's a clearly an overconsolidation, and the divergent curve looks pretty linear, looks really nice. And the other one, you have one of these broad curves, and it looks pretty like the sample's pretty disturbed. So if you want to think about it, Mesri had a lot of the second ones and not very many of the first ones. And so he was using C sub C, he's using the water content as a proxy for C sub C. Because his theory is that there's a relationship between the coefficient of compression and the coefficient of secondary compression. But he didn't have a lot of C sub C data. And you can't screw up water content. At least it's hard to screw up water content. As long as you didn't let the sample dry out between the time you sampled it and when you tested it, the water content didn't change. Compressibility is highly dependent on how you treated the sample. So that's why he developed this. And there's a fair range. And I would also point out to you, again, this is plotted as, what's this scale? And what's this scale? So if you went and plotted that linear curve, you would see a lot more scatter. So there's quite a bit of scatter in that data. So we assumed that C sub C was, I don't want to say directly proportional, but was somewhat related, let's say, to the water content, at least in the same direction. Water content goes up, the compressibility goes up. Okay, and his conclusions are that C sub alpha varies between 0.001 and 0.5, and that epsilon of alpha varies between 0.1 and 10%, except for some really highly compressible peats, which obviously have a very different structure. Peats are really organic soils. It's all about, it's not minerals that are in there. It's something else. And I guess the fundamental thing here that I take out of this is that he demonstrated that there is some relationship between C sub alpha and C sub C, which is to say, if soils are more compressible, they undergo more secondary compression. And in my mind, we discussed this issue of this concept that what's going on if you load a soil past primary, that you're breaking up the existing structure, and it's got to get rearranged. So that if you think about it, the higher C sub C is, the more compression is going to go, with the more structure it must have had before you beat the soil up. And we see that particularly in those highly sensitive clays. I don't know if you can remember back to some of those E-log P curves we showed those, where there's once it crosses the pre-consolidation stress, not in a semi-log plot, that line goes almost vertical. So clearly there's a big structural change there. So if there's a big structural change, then it's reasonable to expect there to be a significant amount of secondary compression. And if you look at places like Mexico City, where they have some really unusual clays, and it has a lot to do with part of the issue with Mexico City clays is it's got a lot of diatoms in it, and it's not typical minerals. And that stuff has a very high secondary compression. That's why the Fine Arts Center there has settled to 2+ meters. It's really, a lot of that's due to secondary compression. So that's kind of the takeaway from there. And then please note that this is a log-log plot. So if you and I looked at it the first time, I don't know if we'd come up with the same conclusion. But all right, and then we'll look at Mesri and Godlewski, and we're going to look at Mesri and Godlewski, and we're going to look at Mesri and I'll think of it in a second. And both those papers are about much more than just secondary compression. I'm just concentrating on the secondary compression part of them. So in this case, they did really high quality tests and measured C sub alpha and C sub C throughout the entire consolidation range. So they did this exercise with using Casagrande's method for every load on the curve, back calculated the end of primary consolidation curve, and they had C sub C and C sub alpha data throughout the entire range for the entire consolidation range for quite a few soil samples. So this solved this problem. He's now able to eliminate water content as the value he's measuring, and actually look at the C sub C and C sub alpha. Okay, and his conclusion from this, or their conclusion from this, is that C sub C over the ratio of C sub C over C sub alpha is a soil property. It's constant for a given soil. So that means, if you think about it, if this is our if we have, for instance, if we have a sensitive clay that looks something like this, you know, you have a very, and when I say C sub C, I just mean the slope of the E log. I guess this, if I'm doing C sub C, this should be E and not epsilon. This applies in a reload part of the curve too. So when I say C sub C here, we're just talking about the slope of the curve, whether it's wherever it is, whether it's in the reload section or the virgin curve. Well, if you take this soil just beyond the pre-consolidation stress here, sigma, the pre-consolidation stress, well, this is really steep here, which means you're going to get a lot of secondary compression as soon as you go past the pre-consolidation stress. So that was his basic conclusion. The other thing that comes out of the paper is that now that he's got much better data, he's got a much smaller range for C sub C over C sub alpha. So his conclusions are that C sub, the range is quite small, 0.025 to 0.1, and actually for most soils it's even smaller than that. And the point you get out of that is from this, if you believe this, this means the shape of the E log PU curve you get is going to be a function of the load increment ratio that you use when you're doing the test. And it's also going to be a function about how far past the end of primary you let the test run. Because in this part of the curve up here where it's really, really steep, if you let all let's say you're doing a 24-hour cycle test, and you let all the tests, and it turns out the soil consolidates in 8 hours. So you let everything run 16 hours past the end of primary, and you're using the 24-hour test data. Well, you're going to get a whole lot more secondary compression in this range, because they're all going to go under approximately the same amount of secondary compression, or the same secondary compression for the same amount of time, right? Well, in this range, you're going to have, C sub alpha is going to be much, much bigger than the C sub alpha from this range down here, where C sub C is much smaller. So right around the point where you got the pre-consolidation stress, you're going to get a whole lot more secondary compression in your lab tests. And we'll talk about the load increment ratio here in a second. But the bottom line, so the load increment ratio, normally when we do a consolidation test, right, we put on a load of X. So let's say it's 1/4 of a ton per square foot. And the second load is going to be 1/2 a ton, and the third load is going to be 1 ton, right? And you're adding, every time you're adding a load, you're adding on the same amount of stress. You're increasing the stress 100 times or 100% or 1 times what the existing stress is. That's the load increment ratio. And you'll see, in fact, Holtz and Kovacs talk about that, is if you use different load increment ratios, you get different E log P curves. And if you believe Mesri, he'll explain why that happens. And part of the problem is sometimes you don't see an inflection point in your curve. Like you guys saw that in some of the data you look like, where there's no inflection point in the curve. Where you can show mathematically that if you have a load increment ratio of 1 or greater, that you always have to have an inflection point. But if your load increment ratio is less than 1, and this is because the secondary consolidation doesn't wait till the end of primary. It's happening all the time. So if you think about it, if it's happening all the time, then if you don't have enough, if you don't put a big enough load on that your primary consolidation is large, then your secondary consolidation your secondary compression can actually be, since that's a function of time, not a function of the load, right? If you run a test a long time and you don't have a large primary, it could be your secondary consolidation is about the same magnitude as your primary, and then you're not going to see that load, you're not going to see that inflection curve. So Mesri would tell you that all those data out there where they don't see inflections have to do with secondary compression and not having the appropriate load testing methods. So Mesri and Castro is the last paper in this, and this is just an update of it's just follow on with better data. So in this one, they had a lot better quality data, and from a lot of natural clays. A lot of the data that came from Mesri and Godlewski came from I want to say recompacted, came from disturbed samples. So they had a lot of data. Notice now this This curve is now plotted on an arithmetic scale, right? It's not plotted on a log-log scale anymore, and that's pretty good fit right there. So now we're looking at a much higher quality data. And these conclusions basically just substantially narrow the range of C sub alpha over C sub C to the point where you probably don't even need to know what it is at least to do a first order of magnitude estimate. So for inorganic soft clays, he says C sub alpha over C sub C is 0.04 plus or minus 0.01. Well, boy, if we knew all our parameters that well, we'd be in great shape. For our highly plastic clays, it's really not that much higher, but 0.005 plus or minus 0.01. Whoops, I didn't mean to. So those numbers are small enough that you should be able to take these values and do a secondary consolidation estimate without even doing any testing. So if you know what C sub C is from your test, you should be able to right away do a quick calculation and figure out whether secondary compression is going to be an issue for you or not. Those are really nice. I mean, would everything was that well correlated for us. So the conclusions that I have. So secondary compression is real. The higher the compressibility, the greater the secondary compression. You got to buy into Mesri's stuff to do this, right? I'm giving you his conclusions. For routine estimates, you can use these data from Mesri and Castro, and then, I mean, this is the approach I would take. I would do that first, and then if it looks like, ooh, this could be an issue, then you need to go do some. Then you need to do some really good lab tests to do that, because it could take a long time to do. To do those secondary tests, you got to run that test out way past primary. You don't want to do it just for one point. If you're gonna try to estimate the value of C sub alpha over C sub C for your soil, you need to do it a bunch of different points on the E log P curve in order to get a value. You don't want to just do one. I mean, wouldn't you guys like to have more tests than you got right now for your project? You got 2 tests, and one of them is clearly bad, and the other one's in the wrong place. So that's my secondary. If you want to get into secondary compression, Mesri's the guy, and he's been doing this stuff for years and years and years. I think it's pretty simple for most stuff. The places when you get into these highly sensitive clays, Mexico City clay, any of the quick clays, it becomes a significant issue. It's a big issue for those Japanese airports for Kansai, and I can't remember the other one. There's a real question about whether they properly accounted for secondary compression and how long those airports are actually going to be above the water level, especially if you got sea level rise. It's a big issue. So if you've got really, really large consolidation, and it's a project where the time is a real big issue there. A bunch of the Hydro-Quebec, it has a bunch of hydro projects in Canada, and many of them are built on highly compressible, sensitive clays, and it's a huge issue for them. You don't want the freeboard to suddenly be 1 meter less than you thought it was because you've been undergoing secondary consolidation for 45 years. So if you're in those situations, it's something to really worry about, and there's the place to go look for information. Questions about secondary compression? Okay.